Hello, welcome to our Helmholtz Coil lab. This is about creating magnetic field when you pass current in a coil, actually. So we kind of talked about solenoids and Helmholtz coils, hopefully in the class. If not, then this would be a good introduction. And I want you to follow this through using your homework and the textbook and the lecture material so that we can complete this lab properly. So what we want to really talk about is about the Helmholtz coil, but I just want to remind you that we talked about magnetic field of a moving charge, which is given as mu naught over 4 pi q v cross r cap, where r cap is a unit vector. It doesn't have a magnitude, it has magnitude of 1 divided by r squared. So if you have even a moving charge, which is basically has a velocity of v, what is the magnetic field that will be created here? Now, you have to use right-hand rule to figure out the magnetic field direction. That's why that cross product is like. So for example, if the velocity is towards that direction, right, and then your r cap is over that direction, so remember that you take your velocity and then you move it towards r cap. So if my velocity is in this direction, let's say, and then I have r cap, which is the unit vector in this direction, so I extend my palm towards the velocity, and then I curl my finger toward that unit vector, and then the thumb will point to the magnetic field direction. So that means that in this case, the magnetic field will come out from the board. So, and this goes as 1 over r square. So the magnetic field drops away as 1 over r square. It also depends on the velocity of the particle and also on the charge of the particle. Then we also talked about magnetic field of a current element. It's if you have a current I flowing through an element which has an extension of dl, we kind of follow the same thing, except right now, instead of qv, you replace it with that current element and the magnitude of the current idl cross r cap. It's really interesting that current itself is not considered a vector, which is kind of, it's strange actually in a way. But the element itself is a vector. So you can get cross product. Look over here, this I is a scalar value. And really speaking, when you do any type of vector calculation, your wire might be all wound up, something like this, but it has a current I flowing through it, 1 amp, 1 milliamp, whatever it is. To get it to a vector form, you actually have to define a small segment of it, and that will have a particular direction. Otherwise, as you can see right here, the current really goes all over the place. The direction changes all the time. So you have to have that current element. And then if you want to have a magnetic field for a big current element or something like that, you have to integrate over all dLs and get the final result. We also talked about magnetic field of a current carrying conductor, where you have, if the line is infinite, what would be a magnetic field at a distance x from it? And that was our derivation, mu naught I over 2 pi x, where of course the x is the distance of the point where we want to measure the magnetic field from the wire itself. And we also talked about the solenoid, where, and remember what a solenoid actually looks like. It's basically a coil wound around a certain cylinder or something like that. We'll show you later on. Helmholtz coil itself is kind of a solenoid. It's just a special kind of solenoid. And we had mu naught Ni as the expression for magnetic field on its axis. Mu naught is magnetic permeability. N is the number of windings, and I, of course, is the current through it. And that brings us to a Helmholtz coil. What we have here are the Helmholtz coils. if you can have it as a single one, or you can have it as a pair formation. So when you look at the pair formation, we go back to, again, we derive it in the class right here. So you have this circle right here, which is basically this circle here. You have n windings in it, and then on its axis, from the center point, you want to measure a magnetic field which is at a distance x from the center. What's the magnetic field there? And you have current I flowing through the coil. Then we derived it in the class. It's mu naught Ni, and you know the derivation is a little bit involved, but I want you to re-derive it for, for this lab. N again is the number of windings. I is the current that is flowing through the, the coil. A is the radius of the coil, right? And then you have x squared plus s squared raised to the power 3 over 2, where x is from the center point to the place where you're measuring the magnetic field. So this is what our baseline here is. What we were trying to do is we're going to first experiment with only one coil, then we're going to put another coil, and we're going to measure magnetic field in between these two coils. But first, what you have to do is to sum up the magnetic field from those individual coils and get a mathematical expression. And then what I will do is that I'll give you some field number, magnetic field magnitude, and I'm going to have my Hall probe, or the magnetic field sensor, starting from the left and all the way through the middle and to the end. And you have to actually draw the magnetic field as a function of distance. Let me tell you here, one thing is, if you're in like an MRI machine, it's basically a big Helmholtz coil where your body is submerged, and you are making some very high Tesla. That 10,000 Gauss is 1 Tesla. So you have about 2 to 3 Tesla. But the main thing here is that you don't have to have the entire, you don't have to have this entire distance filled with the Helmholtz coil. You can just have, for example, 2 coils, and you can have more or less stable magnetic field, the same amount, same magnitude of magnetic field in between those 2 coils. And that was the thing that we want to show, that you would have more or less constant magnetic field between these 2 Helmholtz coils. So at least that is our goal. So what I'm going to do is that I'm going to turn off the lights and go over to our screen and look at the write-up a little bit and look at the procedure. Because you're not here, we're going to actually do all the setup for you. Actually, the setup is what takes most time. You understand that. And it's a pity that you cannot be here. But we'll do our best and show you how to actually connect up all the individual components to get the Helmholtz coil going. So let me turn off the lights. I turn off all lights, right? Okay, thank you. So now I'm going to go over to the screen. So the write-up itself, you will get this from the lab list from the 4B course, and it says magnetic field of coils. And if you look at the introduction, it says magnetic fields of various coils are plotted versus position. So fields versus position is what we are after. Okay. Now, if you look at the single coil, this is the one I actually mentioned on the board, right? Let me go over and grab that meter stick. So there is nothing extraordinary about it, but here is the part that we want to talk about a little bit. So you have these 2 Helmholtz coils, right? You're looking from the side, so you don't see the circle of it, the circular portion of it. So you're looking from the left, for example, and the distance between them is d. And if you take any arbitrary point x from the center between these two coils, you are going to superpose, this is called superposition, of two magnetic fields. The magnetic field due to B1 is given in blue, and magnetic field due to the second one is given in red. So you are going to add B1 plus B2, and basically that's that individual distances from those 2 points, right? So when you add them up, I want to make sure that this is the number, this is the value you get, okay? That's an important point right here. So whether you're going to get this, you know, right there. Also, make sure that this is understandable, or whether that goes with that above figure. Sometimes it doesn't, by the way. So I should warn you. For example, this particular number, I want you to verify that, because we had a previous write-up where that number was a factor of 2 high. So I want you to verify that number when you add them up. This follows the homework problem, and I'm going to show you the homework problem very closely. So let me go back to the homework problem. So this is, if you're looking at this number is 28.67. This is from edition 12, so that might change. So if I'm looking at homework number 7 and click on 28.67, this is basically the homework I'm talking about. So there are several things you need to do. This will be part of this lab. First of all, derive the expression for the magnitude B of the magnetic field at a point on the axis at a distance x to the right of point P. This is exactly what that write-up wanted to do. So you have to find out the magnetic field right over here, okay? So then graph the magnetic field versus x for x equals 0 to x equals a over 2, okay? Compare this graph to 1 for the magnetic field due to right-hand coil alone. So you have to do 1 for the magnetic field in between these two coils, and versus where you don't have the second coil, just do 1 for one single coil. We're going to do this experiment and give you some numbers for it, okay? And then you compare this with your theory. C, obtain an expression for the magnitude of magnetic field at point P. Calculate the magnitude of magnetic field at P at these turns. Then I want you to do this. This gets a little bit tricky. I want you to do the differentiation of the magnetic field and take second differentiation of it and discuss how your results show that the field is very uniform in the vicinity of P. So basically what happens that if the field is really constant, you're going to get a 0 for the differential. And it's a tricky differential, but I want you to follow this through and add whatever you gain out of this to our write-up this time. Okay, so it will be, as you will see, the lab itself will not take much time, but the post-lab work is quite extensive. So the answer to this is actually given. This is one of the odd problems, and the answers are in the back of the book. And I checked another edition. It's still an odd problem in the newer editions. So hopefully you can compare your results with the answers that's given in the book. So that's basically it. I will stop right here. Our next step would be actually go to the experiment and give you some numbers. Thank you. All right, so here's our setup. What we have is one of the coils. It's like a solenoid, as I said. And the number of turns are given on the bottom. It says 500 turns. So Hawada is going to help me writing up these numbers. So there are 500 coils over here. Okay, and what we're going to do first is, just so that we know that we can create a magnetic field, we're going to pass some current through it. And what I have here is one of those magnetic field probe that is very handy. And it, of course, goes through what do you call it, interface, so that I can get some digital numbers on the computer screen. So we are using Data Studio, and a Pasco magnetic field probe is a two-axis field probe. Uses kind of also call it like a Hall probe, and I get two numbers over here. But what we're actually interested is called the axial magnetic field. So when I pass current through it, the magnetic field would be literally on the axis of it. So you kind of look at that meter stick, that's the magnetic field direction. So if I'm passing current, this is the red, basically this is the positive side, and the magnetic field is coming through like that, and it'll be coming out from the coil, and then it kind of turns around. Over here, it's the value of it is quite low, but in any case, it comes back and joins it over on this side. So you get a full circle. You can think of this also like the Earth's magnetic field. You have a big dynamo close to the center of the Earth, and the currents are going like that, and you have that north and south pole. Not exactly though, because I'll explain that in the class, because Earth's magnetic field switches every million years or so. North becomes south, south becomes north. Right now we are in a time where the magnetic field is decreasing, the Earth's magnetic field. So then what we have here is, of course, a power supply and a DC power supply, and it can provide a stable current. And we were going to pass 1.5 ampere current through here. So first, I want to just turn down the current all the way to 0. And what I also want to tear it. It basically means that I'm going to make this 0 over here. Let's see. It's kind of, you see that it kind of goes to 0 momentarily, and then it comes back. That's all I need. So it's more or less, I have calibrated it. And then what I would do initially, just to show you that the amount of Gauss is really low. You know, it's we have what you call it, the Gauss on this side going perpendicularly is actually much higher than this is about 0.2 over here. See, it's fluctuating, so the numbers are really low. So what you notice that now, if I increase this current, this thing is going to go up. Now we have 1.27, say 3, 4, 8 Gauss, 10, 12, and this is half an amp going up, 17, 19, and that's 1 amp. I'm all the way up to 28 Gauss. Now I'm going up to, so that's 1.5 amp current. That's what we're using. And you can see that it has gone all the way to like 43 Gauss. What I'm going to do now is measure the magnetic field starting from a distance of 30 centimeter from the central point. So what I'm going to do is like as if you are in the lab. So you're going to measure it, and your lab partner is going to write it down. And Hawade is going to help me. I'm going to get numbers from here. And I will do it every 5 centimeter. Every 5 centimeter. All right. So, so let's, oops. Okay, let's see. Let me first see if I'm getting it correctly. Okay, that's good. All right. So 30 centimeter, it's 1 point, let's call it 1.75 Gauss, 30 centimeter. Okay. 25 centimeter, it's 2.45 Gauss. 20 centimeter is 4.6 Gauss. 15 centimeter, it's 8 Gauss, let's say. Then 10 centimeter, it's 15 Gauss, 15.5 Gauss. Then 5 centimeter, it's 30 Gauss. And 0 centimeter, it's 42 Gauss. Then I'm going to go to the other side. Minus 5 is 31 Gauss. Minus 10 is 16.5 Gauss. Minus 15 is 8.75 Gauss. Minus 20 is 4.7 Gauss. Minus 25 is 2.65 Gauss. And minus 30 is 1.6 Gauss. All right. So that's the first part of the experiment. I just wanted to show you one more thing. We talked about solenoids, of course, and the solenoid looks like this, and it's another experiment. We actually use the solenoid to create magnetic field. The thing I wanted to tell you is that even though when you derive it, we assume that the magnetic field is the same inside it, but that's not the case. Actually, it's highest inside, and then it drops away on the side. And for an 1 amp, it's about 40 Gauss or so right at the center. Okay. So the next part of the experiment, we're going to kind of continue with the same thing, more or less. I'm going to turn the ampere down, and we're going to use 2 Helmholtz coils. So I'm going to take off the wires from here, okay? And then this is actually, you feel this, it's pretty warm right now, quite hot actually. So if you think of that you're eating a heating coil or whatever it is, that's basically it. This is pretty insulated, so you're not going to get shocked, but the heat energy is there, just like a water heater or something like that that you use. So I'm going to take this out. We wrote down this is 500 turn coil, right? Okay, thank you. And 1.5 ampere. So, right, thank you. So right now, what I have here is the 2 Helmholtz coil. They are apart. They will be apart by they're apart by 20 centimeter. Okay, from coil to coil, they're 20 centimeter apart. So that's one thing we need to write down, 20 centimeter. And we're going to use the same method. So what I'm going to do is I'm going to place it, because we're going to measure it also the same way. And I want to go also, again, I want to go all the way to 30, starting from 30 centimeter. Okay. And so it will be 30, then the 20 centimeter here, so which is 50 centimeter, and then all the way to, I'm going to measure it down to 50 plus 30, which is, let me just check here. So I have 0 here. I'll start with 0 right now, so make sure that we understand that. I'm not going to do the same way as last time. I'm going to start at 0 centimeter, then 30 centimeter will be the center of this guy, then 40 centimeter would be the center of both of them. Remember that, 40 centimeter will be center of both of them. 50 centimeter would be the center of the others. We're going to write this down. And then we're going to 60, 70, and we're going to go to 80 all the time. For some reason, it looks a little bit bigger, larger than that one, but I think they're possibly the same. All right, so let me put it here. We're also going to use 1.5 centimeter as before. So one thing is, it's a little bit tricky, and when you are here, this is sometimes it takes to figure this out. So this is what happens. You'll see the current, we will monitor the current, what happens there. If I, let's say that I'm going in here, okay? So the current goes here, you know, turns around and comes out here, okay? So what I want to do is I want to take another wire, take it from here. What I want to do is that the current in the second setup has to have the same direction as the current in the first one, okay? So sometimes we get confused actually which setup we want. So remember, the current goes this way. I want the current go that way also. So I'm going to connect it, see that over here on this side, So that's kind of important, all right? And once I have that, this one comes back to my power supply from here, okay? So that now I have both of them. So what I want to show you, actually, before I do this, I want to show you something else. And this is what I want to show you. I want to just keep one of them. I just want to keep one of them. And I want to go back to that 1.5 setup, all right? So 1.5 amp setup. You can't see that monitor here, but I have 1.5 amp set up there. I'm going to turn this off, and when I turn it back on, it goes back to 1.5, okay? So, and now, this is what I'm going to do. I'm going to go back, attach both of them, okay? And I turn it on. What I have is not 1.5 amp, I have 0.75 amp, because now the current is being shared by two of these coils, so that drops, okay? I would try to, this is a, what you call it, there is a current limiting setup. I'll try to make it up to 1.5 again. Let's see if I can do it. It's a so it will not allow me to do that. So I'll just go back to 0.75, okay? And all right, so I will keep it and at 0.75. And we will now do this, do the same experiment, which is starting from here. Let me just first check.
Do you need to tear that again?
I can tear it, yeah. Thank you. It's not. I mean, we did it once, so it should be still okay, but we tear it again. Thank you. So Now my current is actually going in a different direction, so that's why you get a negative number, so we will not worry about it. But what I want to see all right, so what I'm more concerned about is that they both should have the same direction. So once I come over here, it does drop a little bit, but then it comes back up again. Okay, and right here, it's from 22. I was hoping it wouldn't drop that much, but you can see that it's kind of stable over here. But if I come out here, it drops right away. You can see that. And here, it does drop, but it's more or less a stable number. You see that 16, 17, 18? That number is more or less stable. And then it goes up again when I come to the center. What I will do, I'll first have one set like that, and then I will reverse the current and see what will happen. Okay? All right. I will have either ready. Great, thank you. So we'll start with 0 centimeter. Okay. And don't worry about the negative sign. It's basically the magnetic field is in the other direction. That's all. So 0 centimeter is 1.2. 5 centimeter is 1.8. 10 is 2.8. 15 is 4.5. 20 is 8.7. 25 is 16. And 30 is 24. And if you can write that down, it's a center of the first coil. Center of the first coil. And then 35 is 20. 35 is 20. Then 40 is 16. Actually, you know what? I'm going to give you, after 35, a number of points. 35 is 20. 36 is 19. 37 is 18. 38 is 17. 39 is 16. 40 is 16. 41 is 16. 42 is 17. 43 is 17. 44 is 18. 45 is 20. And then 50 is 24. We got all of them, right? Great, thank you. Now I'm going to go to the other side. 55 is 19. 60 is 10. 11 rather, 11. 65 is 5.5. Then 70 is 3.2. 75 is 1.8. And 80 is 1.3. That's wonderful. I think we got enough material for a graph, good graph. And you can see that I went by 1 centimeter at the very center because that was our goal, to show that at the center it doesn't really drop. It should be flat more or less. We got about 16 and 17 Gauss at the very center, which is good. So the last thing I'm going to do is I'm going to turn this current around. So all I have to do is to switch my electrodes. I'm going to turn it around. And all I want to do is to look at the very center. Okay. Okay, so you can see that the magnetic fields now are colliding in a sense that one opposes other, and the superposition principle holds. So this would be a second set with currents reversed. Currents reversed. And we don't want to go basically, we don't really need to do all this from here. I can go right from the center and see what happens. So 30 centimeter at the center. Oh, I want to make sure. Yes, both are 500. Sorry, I was panicking. I have 500 here and 200 there. That won't work. But we know that the magnetic fields are the same more or less, so it is 500. So they're slightly off. You can see that one of them. It could, there could be many different things can happen. I'm not maybe measuring at the right point. So 30 centimeter is 20 Gauss. 35 is 14. 36 is 10. 37 is 8.5. 38 is 6.0. 39 is 3.8. 40 is 1.2. 41 is 0.8. 42 is 2.4. 43 is 4.8. 44 is 7.7. 45 is 9.8. And 50 is 20 Gauss. So what you notice that actually there is a big dip right now, because when you add both of them, the directions are separate right now, and so they're kind of that's the whole idea of superposition. Minus 20, and over here you notice that right here I get minus 19 or minus 20. Over here I'm getting plus 20. So we reverse the magnetic field right here. You see that just by reversing the current. So I think we got enough information here. What I'm going to do next is that I'm going to turn off the power supply, and I'll go over to the board and write this down for you. So one way of doing this lab is that when I'm shouting out those numbers, you can think of yourself as a participant in the lab and write that down. I think that works better, like as you are really taking the experiment. But I don't want to take any chances, so I'm going to write this down on the board again, okay? Okay, so let me write down these numbers for you. We'll first start with a single coil, and what we need is that we have 500 turns, and so that's your value, N value, and your I value is 1.5 amp. And you can actually, that's enough information to really figure out what should be the magnetic field on the axis. Actually, we're only looking at the axis, by the way. So what we have here is we're going to go, remember for single coil, so this is the coil, we're going to go 30 centimeter one direction and the 30 centimeter other direction. So we'll start with, so this is 30, this is centimeter, and this is in Gauss, okay? So this would be 1.75 Gauss, and then we have 25, we're going every 5 centimeter, 2.45 Gauss. We're going to 20, 4.6, 15 is 6 point, sorry, it's 8.0, 8.0, that's 8.0. Then 10 is 15.5, that's 8 by the way, 15.5. Then 5 is 30. And then the 0, this is the center, we are up to 42 Gauss. So this is the center. So now, so that's 0 right here. Now we're going to the other side. So we go -5. Again, this is centimeter, and that's Gauss. -5. In principle, it should be repeat of this. Hopefully, I got the right number. So 31. This is great. This is -10 is 16.5. We have 10 over here was 15.5. So we're okay with this. -15. We got 8.75. If I look at 15 over here, it was 8.0, so we're all right. -20, I got 4.7. I look +20 up here, 4.6. Very symmetric. -25, I got 2.65. We had 2.45 over here. And -30 is 1.6. And we got 1.75 over here. So these numbers are quite symmetric, you can see. So I want you to draw it. I know you'll get a hump at the center right here, which is 42 Gauss. And what I want you to do is do two things. One is you are going to, so this would be your value of x, and that would be value of b. So you want to do two things. One is that you draw your data points like this, right? And however that would be. But then what I want you to do is that do the theoretical graph. So this would be theory, and that would be your experiment values. So I want you to compare them directly with that graph, right? Okay, so that's for single coil. I'm going to erase it, and if you always can come back to this later. So now I want to do with the double coil. So this is the double coil, right? All right. Now here, what we did was we started going from 0 to centimeter, 0, 25, 30. So we started 30 centimeter this way. And then remember, this is 20 centimeter here. And then we got another 30 centimeter that way. So if I'm coming from the right to here, I started with 0 here. So this would be the 30 mark. This would be center of one of these guys, center 1. And right here, it would be 50 centimeter. It would be center 2. So I'll start with 0, and I'll end up at 80. Make sense? So 0, 30 centimeter, center of 1, then go through that 20, and then go again. The 50 would be center of 2, and then 80 centimeter I'll end. Make sure that in your graph you make these distinctions. Okay. So this time my ampere, which is I actually, I would be 0.75 amp. Okay, and each one of them again has 500 turns. N is 500 turns. All right, so let's. I want to go a little bit further to the left. So we have centimeter, and we have Gauss. So 0 centimeter is 1.2. 5 centimeter is 1.8. 10 centimeter is 2.8. 15 centimeter is 4.5. 20 centimeter is 8.7. 25 is 25 is 16, and then 30 is 24, and this is the center. We arrived at one of the centers. Okay, and then 35, we got 16. And then we took a series of 1 centimeter measurement. After it kind of dropped right there, we took a series of 1 centimeter measurements. So 36 is 19. 37 is 18. 38 is 17. And you can see that this is dropping, but it's still kind of stable. It doesn't drop that much. 39 is 16. 40 is 16. 41 is 16. 42. My apologies. Where is it? Oh, this must be in here. My apologies here. All right, so 42 is 17, and 43 is 17. Then 44 is 18, and 45 is 20. Okay, so I'm not done yet. What I have done is actually, right after 35, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 numbers, 1 centimeter apart, just to show that this is how stable that Gaussian field is, I mean the magnetic field is. And then I'm going to jump to, again, to our 5 centimeter thing. 50 is 24. 55 is, now remember this is my center. This is center 2. And I go back here and look at that 30 centimeter was my another center. It was 24, and that's back to 24 again. So 55, and the other part should be symmetric. Let's say 55 is 19. Okay, it's a little bit off from the other side, but that's all right. So 55. 60 is 11. 65 is 5.5. You can see how quickly it's dropping. 70 is 3.2. 75 is 1.8. And 80 is 1.3. All right. So again, you need to do a graph, which is the data points, and then you have to do the theoretical graph, right? So just so that you know what that is, I can go B and X, and the graph would come out, the theoretical graph would be coming out like that, but your data point could be like this, also, you know, could be like that. So you want the data, experiment data, and you want the theory. So you want to actually draw both of them. You can do it by hand. You can use Wolfram alpha, for example, to do this. So the next thing we did was actually reverse the current in the second coil, so that when you add them up, it will come close to 0. So let's see if that happened. In this case, we started at from the center, and then we just took the data only in the center point, along those 20 centimeter, right? So I'm going to erase this, and you can always come back to it, so that's not a problem. All right, so 2 coils with reversed current in one, and so the B fields are opposite each other. Actually, I want to do something very quickly. this is okay. We can continue with this. I want to actually go back and take a look at my direction of the B field. So we said that this is the minus 20, and then as you go through it, it's minus. So right here, see that? And I should have remembered it to do it at that time. What I want to do very quickly, and Awada did such a nice job here, but I didn't tell her everything. I just need the pen right there. Thank you. So what I want to do is just show that where it reverses. So I got minus 20 here, and then it goes down to 40 is minus 3, 8, okay, minus 1, 2. And then right here, which means from 41, it becomes plus. So that's where it changes. So right there in between, you have it goes to 0. So that's the only thing I wanted to, and I should have been careful in mentioning that, because the field does go to 0 all the way down at the center, and then it switches. It becomes from negative to positive. So okay, so I have 30 centimeter. This is the center of one of them, which is, this is the Gauss, minus 20, so it's only along one direction. 36 is minus 14. 37 is 20 minus 14, and then 36 is, sorry, I needed 35 here. That's 35 is minus 14. 36 is minus 10. 37 is minus 8.5. 38 is minus 6.0. 39 is minus 3.8. Then 40 is minus 1.2. I'm right at the center, and this is where it switches. And look at this, for 41, I'm getting plus 0.8. That's it going through 0 right there. And it changed direction. So 42, now the other side becomes stronger. This is all plus 2.4. 43 is plus 4.8. 44 is plus 7.7. 45 is plus 9.8. And 50 is plus 20. I'm back to 20. There's a little bit of difference between, it's not exactly symmetric, but part of it is because I'm not pointing at the right at the center. But I want you to do exactly the same thing again. This is the theory part which was not mentioned at the beginning because we were only looking at the positive, adding them up, but this is the subtraction. And as you can see that it drops to 0. So literally, you're talking about something dropping to 0, then coming back up like that. So you want, again, to do both of them, both for the theory and experiment, both of those two graphs. I think that I wish you were really here in the lab, and you can see that there are a lot of different parts to this lab. It looks pretty straightforward, but the math is a little bit complicated. And I hope between that homework problem, the exercise problem, and the lab problem, you really got some insight to how these coils actually work. And they are everywhere, actually, in our life, as I said, from creating a stable magnetic field is, we always want a stable magnetic field. And it covers physics experiments, like particle physics accelerators, and involves medical physics. So a lot of different things. I'll see you in class. Thank you.